Now that we know something about impedance and how it works, we're going to talk about voltage and current in AC circuits. We've talked about how to find impedance, and we pretty much, if we look at AC circuits, they're really pretty much the same as DC circuits. The only thing we have to consider is the fact that all of the numbers are complex numbers at this point, and that there is a frequency dependence to the elements in the circuit. Anything that we've learned so far as that can be used in circuit analysis, Ohm's law, KVL, KCL, nodal and mesh analysis, Thevenin's theorem, superposition, all of those work the same exact way with AC circuits. The process in this class of nodal and mesh analysis we don't tend to do because we don't want to make you do matrix equations with complex numbers, but you could if you wanted to. You could do all the same processes that you've learned so far. The one thing we're not going to do yet is we're not going to talk about AC power. Power is a little bit different in AC circuits, so we're going to handle that separately and later. So right now we're just going to talk about voltage and current. So remember last time we talked about the fact that voltages and currents can be presented a couple different ways. You can have a time-based formula in which the voltage is time-dependent and includes a frequency. In this particular equation, we've just used the radian frequency of omega, which equals 2 pi f. Most of the time, you'll be given a frequency in hertz. But if you're given a time-based equation, just remember that the number before the time is actually 2 pi times f. We can also get a magnitude and phase angle, and the voltage will be given as a magnitude times a phase. The current will be given as a magnitude times a phase. And the magnitude can actually be either a peak value or an RMS value, which we mentioned last time but really didn't talk about what that was. So there are three different ways to represent magnitude of a voltage or a current. First of all, we can measure the peak-to-peak value. That's where we go from maximum to the minimum, or the difference between, and that gives us the value that would be the peak-to-peak value. The peak value is measured from 0 to either the positive or the negative peak. It doesn't matter because the peak value is a absolute value, so we don't worry about the sign. We just have the value, the distance between 0 and the peak. So also, it probably goes without saying, but I'll say it anyway, that the peak value is always half the peak-to-peak value. So if you happen to know the peak-to-peak and you divide by 2, that would give you the peak value. The other way it can be represented is the root mean square value. And the root mean square value is going to be calculated using 0.707 times V peak, and we'll talk just a second about where that comes from. But the average value, you'll notice the average value was shown on that diagram also, but the average value isn't really very useful to us. We can take the average value of a sinusoid, and we don't really have any use for that because it just tells us what the average of the waveform is, but it doesn't really tell us anything about how it affects the circuit. The root mean square value has a meaning, and it actually translates into something that affects the actual circuit. So the RMS value of an AC waveform is defined as that value that gives you the same amount of power to a load resistor as an equal DC voltage. So when we figure out the RMS value of a waveform, that's basically a value that we can relate to a DC voltage that would produce the same amount of power. RMS values are, if you ever use a digital multimeter to measure AC voltage, the value that you get is the RMS value. So if you go and measure the voltage coming out of the wall, you will get the RMS value of the voltage being delivered to your house. You won't get the peak value, you just get the RMS value. So we sometimes also call this the effective value, and the reason we call it the effective value is because it has the same effect as the equivalent DC value. The definition of how to figure out the root mean square value is to take the square of whatever function you have, integrate it over one period, and then divide by that period and take the square root, which is basically the root mean square process. The nice thing is we don't have to do that every time. We actually have already a way of calculating it for sinusoids, but if you had a value or a waveform that was not a sinusoid, you would have to go through this process to figure out the RMS value. So when you have a time-based formula, the magnitude that you're given is always the peak value or the amplitude. So if you're given a time-based formula, whatever the constant before the sine or the cosine, that's always going to be the peak value. If you're given the magnitude and phase, the polar value for voltage and current, then the magnitude might be RMS or it might be peak. In this class, assume that it's the peak value unless I tell you or the problem tells you that the value is an RMS value. We basically use an approximation formula to find the value of RMS value, and we approximate that by taking 0.707 times the peak value, and we will use that if we have a sinusoidal waveform, which we pretty much always will in here. So now we're going to look at how AC voltage and current works in different elements in a circuit. So first of all, in inductors, remember that when we had a changing value of current for inductors, we could have a voltage across it. So in a DC circuit, an inductor would charge up to a certain value of current, and then when it got to that value, there would be no voltage because it basically reached its maximum and it was done charging. So what happens in an AC circuit? Well, in an AC circuit, the current's always changing because it's a waveform that gets positive and negative and positive and negative. So there's always voltage across the inductor. The voltage, though, still depends on the derivative of the current. So let's say that the current is equal to some peak value of current times sine omega t. And that's a pretty simple way to represent a sinusoid. So the voltage then would be the inductance times the derivative of that sinusoidal function. And when we take that derivative, we bring out the omega because that's multiplied by t. And we take the derivative of the sine, which is the cosine. And we have omega L, I peak, cosine omega t. Now, notice that the omega L is actually the impedance of the inductor. Since that's how we would calculate it, we do 2 pi f times L. So we have the impedance, and that impedance is actually multiplied by a current. So we can actually take that whole number and turn this into just a voltage value. We can turn that into a peak voltage. We can also change the cosine to a sine so that we can compare it to the initial value. And when we do that, we get a peak value of voltage, whatever that would be, times the sine of omega t plus 90 degrees. Well, what this means is that the voltage is actually ahead of the current by 90 degrees. But we don't actually talk about voltage being ahead or behind current. We usually want to say what current's doing with respect to voltage. So we switch that around and we actually say that the current lags the voltage by 90 degrees. And to sum all that up, you can see that in an inductor, when you have an impedance for the inductor, that impedance is going to be either an imaginary number in its rectangular or polar form. And if we assume the voltage has an angle of 0, and we use Ohm's law to figure out what the current would be, we end up with the current being having a phase angle of minus 90. So you'll notice that the inductor current actually crosses the 0 axis 90 degrees later than the inductor voltage. So the current is lagging the voltage. Now, in capacitors, this is going to look very similar because this is basically very similar. We've just switched current and voltage around. So in a capacitor, the current will depend on a changing value of voltage. When we looked at a DC circuit, we had capacitors that would charge up to a certain value, and then once it got to that value, there was no current going through it. So in AC circuits, we have a similar thing than we did to inductors. The voltage always changes, so there's always a current through a capacitor, and the current still depends on the derivative of voltage. And again, this will look extremely similar. We're going to let the voltage of the capacitor equal a peak value times sine omega t, and then we're going to take the derivative of that value, multiply by the capacitance to give us the current. And when we do that, we get omega c d peak cosine omega t. And now, instead of impedance, we actually have 1 over the impedance. We have omega c, which, remember when we calculate the impedance of a capacitor, it's 1 over 2 pi fc, or 1 over omega c. But because we have 1 over the impedance, we can actually multiply that by d peak and get a current value, since voltage divided by impedance is going to equal current. And then we can again change the cosine to a sine, and we get I peak omega t plus 90 degrees. And this time we don't have to switch the leading and lagging around because the current leads the voltage by 90 degrees. So, summing that up, we get, again, exactly as we did with inductors. This time the impedance has a negative 90 phase angle. We can still assume the voltage has a phase angle of 0. And when we go through and find the value of current, it is an angle of 90 degrees, which means it is crossing the 0 axis 90 degrees before the voltage. So the current is ahead of the voltage by 90 degrees. Oh, what about resistors? Well, resistors are always in phase. Resistors don't have a phase angle because they're just real numbers. So we can represent a real number either as just the magnitude or the magnitude of an angle of 0, and they mean exactly the same thing. So if there is not an angle of 0 after the magnitude, it doesn't matter because it basically means the same thing. So we just take the voltage having a 0 degree angle, we take the voltage divided by the resistance, we get the value of current. Current has a 0 degree angle because current is in phase with the voltage for a resistor. So we're going to look at an example, and we're going to look at some of the things that occur when we end up dealing with AC circuits, and we're going to look at something really simple to begin with. In fact, if this were a resistive circuit, I'm sure you would have no trouble finding the voltage across any one of those elements or finding the current. And actually, the process that we do, even in an AC circuit, is not that difficult. So first of all, we want to know what the total impedance is, and all we need to do is add up the 3 values because this is a series circuit. So we get 100 plus J200 minus J400, and we get 100 minus J200 ohms. And we're also going to represent that in a polar form. Calculator will change that over, or you can do it the long way if you really, really want to. But that gives us the polar form because in order to calculate the current, we're actually going to use the polar form first. And we just use Ohm's law to find the current. So we take 50 at an angle of 0 and divide by 233.61 at an angle of minus 63.43. And we get 0.214 at an angle of 63.43 amps for the total current. So we're going to sort of set those off to the side. And we also represented the rectangular form of the current, just in case. It's a good idea when you're finding these values to just go ahead and note what the rectangular and the polar forms are, just in case you need one or the other. It's easier to do it when you've got it rather than try to do it later. So we're going to just use Ohm's law this time. We could use the voltage divider rule if we wanted to. We could do that, but we're not going to do that today. It works. But we're going to use Ohm's law because we already found the current anyway. So we take the current in the 100 ohm resistor, multiply it by 100, we get 21.4 at an angle of 63.43 degrees volts. For the J200 inductor, We do the same thing. We take the current times the impedance, and we get 42.81 at an angle of 153.43 degrees volts. And again, if you have a calculator that will do these calculations, that's fine. But if it's in polar form, you can just multiply the magnitudes and add the angles, and you'll get the answer. Then for the minus J400 capacitor, we take again the current times the impedance, and we get 85.61 at an angle of 26.57 degree volts. So we're going to set those values aside also. And here is where sometimes dealing with AC circuits is a little difficult, because there is really no way of knowing if those numbers are correct or not. There's not a way of intuitively knowing that they might be correct. In a DC circuit, you can look, and if you've got 30 volts being supplied and you get values that add up to 30, you can pretty much just look at it and know that whatever voltages you got would be correct. You can do that with these as well. So what we're going to do is we're going to use Kirchhoff's voltage law, because the voltage drop across each one of these elements should equal the source, and we're going to add those three voltages together and see if we can get 50 at an angle of 0. And we don't. We get 47.86 at an angle of minus 0.005 degrees. So is that wrong? It didn't add up to 50 at an angle of 0. Well, let's go back, and instead of using polar forms of numbers, let's go back and do the problem. And it works well with this problem. Not every problem works well this way, but let's go back and just use rectangular numbers, because the rectangular numbers were actually nice round numbers. And if we do that and use Ohm's law again, using rectangular values this time, we get 10 plus J20 volts for the 100 ohm resistor. We get minus 40 plus J20 volts for the inductor, and we get 80 minus J40 volts for the capacitor. And when we add those up using KVL, we get exactly 50 volts. So what happened? Why didn't it add up when we used polar numbers? Well, basically because when you're using polar numbers, oftentimes, not all the time, oftentimes there is a significant amount of rounding that goes on when converting from rectangular to polar. And because of that rounding, when you add all the values up, you don't get exactly what you started with. But what we got was close enough. If you were to add all the values up, especially since the phase angle is very close to 0, we can assume that that is probably correct. That's one of the things that you really do need to pay attention with AC circuits, is making sure that things add up the way they should. And when they add up, basically you're just going to have to go in and do it with a calculator. You can't usually go and do it in your head. It makes it a little more difficult. So there will be, the next video will show some problems and how to use all of the tools that we've used so far to analyze the AC circuits. We'll look at a couple of examples, and then of course your homework will give you practice as well.